diving back into enthalpy of neutralization reactions, we've been trying to focus on the actual neutralization reaction that takes place. So we've been talking about how these sodiums and these sulfates, they're just spectator ions. And we'll circle back to that a couple times in this video. So this is our actual reaction that's taking place. Some people still like to write out the sodium hydroxide plus H2SO4 going to, sodium hydroxide and sodium sulfate, I should say, plus 2 waters, 2 H2O. Okay, and I need 2 hydroxides to balance that. Anyway, people are still hung up with that. I'm telling you that 2 sodium ions are spectator ions. It's 2 sodium ions here. And I got 1 sulfate ion here at the start, and it's 1 sulfate ion here at the end. I call them all spectator ions. They're not participating in the actual reaction. Okay. Right. So all I got to figure out is how much hydronium do I have, how much hydroxide do I have, and which one's limiting how much water I form. My moles of hydronium is going to be equal to 2 times my moles of H2SO4. If you're not comfortable with that, it's because sulfuric acid is diprotic. It's got 2 protons to give. So I'll quickly draw it out. If you put sulfuric acid in water, it would already have bumped into water. I'm kind of glossing over the fact that this is a strong acid / not a strong acid. Talked about that previously. I'm going to do a strong arrow for me for right now, and sorry, I'm balancing it live. I shouldn't balance it. I need 2 and 2. All right, and I'm saying for each water's going to steal 1, then water's going to steal another. I'm going to make 2 hydronium ions. So for every 1 sulfuric acid, I get 2 hydronium ions. And I go 2 times C times V equals 2 times the concentration times 0.02, which is 5 times 0.02, which is 0.1 mole. And so I got 1/10 of a mole. Moles of hydroxide equals my moles of sodium hydroxide 1:1. It's because sodium hydroxide has already kind of split apart into its sodium ions plus its hydroxide ions. So when you're picking up a bottle, it's already in this kind of form. 1:1 relationship. C times V. Concentration equals, where is it? 1 times 0.05. It's going to be 0.05 mole. And after we've worried about the 2, you can see that this guy is the limiting reagent because we're saying essentially 0.05 of him reacted, therefore we're going to get 0.05 of him react and 0.01 of him formed. And so the moles of water formed or produced, or whatever you want, is going to be equal to 2 times the moles of my limiting reagent equals 2 times 0.05. And you might notice I didn't really do this step last one, so just to finish this off with 0.1. And that's because we're talking about the definition of enthalpy of neutralization is the energy released per 1 mole of water formed. So I got to come back to this and go, well, moles of H2O per 1 mole is going to just be equal to 0.1 divided by 2 equals 0.05. Now, I don't normally do this, but I've kind of reflected on the fact that I really should. So I'm just doing one of those things where I assume the marker, which I'm often the marker would know what's going on. But then I was thinking about it from a HSC perspective. If they're looking at it, they'll probably pick up and say, technically, this is incorrect chemistry. So I've kind of gone back to doing this. And you'll notice that it kind of is a useless step because you times it by 2 and divide by 2, but lo and behold, it's necessary for the answer to be correct. So this is 20th of a mole of water formed. This is basically per mole of water formed this is how much water formed, and then I got to figure out how much energy was released by that reaction, or released by that much water, or released during that much formation of that much water. And I do Q equals MCAT. I'm going to use the subscript of W to remind you that we're focusing on the solution, the water, the solution. We're focusing on how much energy it absorbs. Now we're going to do the mass of the 50 mils and the 20 mils, which we assume to be density of water 1 gram per 1 mil. So we can basically just go 70 grams, 50 plus 20. We go 4.18 joules per gram per Kelvin. Some people like to use these units a bit differently, and that's fine. It's up to you. Just a bit of a note on that. We have to use the specific heat capacity of water. This tells you that it takes 4.18 joules to get 1 gram of water to go up, to move or jiggle a bit faster, that we call 1 Kelvin faster, a speed faster. And because we don't know the specific heat capacity of the mixture, we're just going to have to assume it's water. And difference in our temperatures is difference between 29.8 and 22.3. And go Kelvin, and they're going to be equal to 2000 odd, 70 times 4.18 times 10 odd, 29.8 is 22.3. Yep, 2194.5. Sorry, it's not in kilojoules, it's in joules, and I want to get into kilojoules. And we go, right, this is how much energy was released. And I go change in H equals negative Q on N. My negative Q is my number I just calculated, 2.945. And my N is the per mole of one formed. So I could write this as moles of H2O per like 1 mole or something like that. As long as I'm getting the numbers right. 0.05 equals, divide that by 1,000 first on my calculator. Open 0.05 equals negative 43.89. Yeah, because I got to round it to 3 sig figs, because everything in the question is 3 sig figs. Yeah, boom. Okay, good. So just a quick reflection on what's highlighted in yellow. I should start adding that to my answers. Now, we're going to focus on this hard question, which is kind of got a lot going on. Okay, and you can see I was just doing a working out before. All of this working is relevant to that. Before I take you on that journey, we're going to go over 2 other questions, which I've kind of made up, inspired by a HSC question. It's like, can't remember, roughly 2020 or 2021. And it was like roughly question 30, although don't quote me. And what they were looking at is they gave you a bunch of reactions and they gave you these enthalpy changes. And obviously they're the same, this one's different. They're kind of going, well, what can you point to that's explaining this difference? And it says it's not an issue with the experimental method. So what's going on here? First thing that you should notice is that this is a strong acid. Okay, so I might just do it in green, it goes over. Strong acid, strong base, strong acid, strong base. And this is a weak acid and a strong base. Okay, and so the weak is something most kids should be able to get a mark by really pointing out the fact that acetic acid is a weak acid, and that kind of must be the reason why it's different. But we're going to go a bit deeper than that. We've got 4 marks worth of stuff. We also got to explain why these are negative 56. The reason why these are negative 56 is because they're doing the actual, both of them, the only thing they're doing is the actual reaction. And if you do a strong acid and a strong base, everything's already in this form. So when you pick up a bottle of HCl, that HCl, if you put in solid HCl, that solid HCl will firstly dissolve into aqueous, and that aqueous would bump into H2O, and it would be H0 plus chlorine minus. And so when you pick up the bottle, everything's already in this form, right? And for sodium hydroxide, everything's in this form, okay? And the only reaction that happens is when the hydronium ion and the hydroxide ion bump into each other, okay? And similarly, H2SO4, we've got sulfuric acid would already be in the form of this. Yes, it's diprotic, so I'll do two of them like this. We've talked about it kind of not being a strong acid, but it kind of is. And also the thing I want to keep in the back of your mind is this idea that if you have a weak acid or a weak base, they will fully react with a strong acid or strong base if there's enough of the strong acid and strong base in terms of moles. Okay, so you could have a weak acid like, where have I gone? Weak acid like acetic acid, but it can fully react. 1 mole of acetic acid would fully react with 1 mole of sodium hydroxide. Okay, you get 1 mole a liter, 1 mole per liter, right? And that's fine. We've got to explain why that happens too. Going back to what I was saying, when you pick up your hydronium, your sulfuric acid, it's already dissociated. So you're basically picking up a bottle that is hydronium ion and sulfate. When you pick up sodium hydroxide as that, and you should be able to now see the similarities between those two and figure out why this reaction is the only reaction that's taking place. And experimentally, it's always around -57, -56 kilojoules per mole. It's kind of like the accepted value for neutralization if it's a strong and a strong. Okay. And that's kind of what you got to get into your answer, that these are both doing the same. Now, the other thing that you want to focus on is the definition of neutralization, which is per 1 mole of water formed. Now, the harder thing to understand, because you forget about everything in year 11, in module 4 in particular, I want to put two things in your mind. Enthalpy changes. You learned quite a few formulas. One aspect you looked at is the energy of breaking bonds, or the summation of the energy of breaking bonds minus the summation of the energy that you get back from forming bonds. Okay. And then the other thing that you learned is the enthalpy overall is going to be a summation of all the enthalpy changes. Okay. Of all the enthalpy changes. So you might get, probably just get like something like this: change in H of reaction 1 plus the change in H of reaction 2 plus the change in H of reaction 3. Okay. So we're going to get towards, we've kind of got 3 enthalpy changes that we need to keep track of. We've got the enthalpy of neutralization that we want to keep track of. We got the enthalpy of ionization, which is going to be our focus for explaining the ionizing. Like, you have to break the hydrogen and make it into the ion first, and you need to worry about that energy change first. And then what's not in the top question, but it's in the bottom question, is the enthalpy of dissolving or dissolution. So the enthalpy change of breaking these ionic bonds and then getting it to dissolve and forming ion dipole bonds. Okay, so we kind of got to keep track of all that. So to be more clear, this is change in H of neutralization, this is change in H of neutralization, and this is change in H of neutralization plus the change in H of ionization. Because you already know this to be -56, you can infer that this must be +30 kilojoules per mole. This is like the shortcut version of looking at these things. If I go down to here, you got strong acid, strong base, strong acid, strong base. The only difference between reaction 1 and 2 is the fact that sodium hydroxide is a solid and that one's in aqueous form. So this is the change in H of neutralization. That's why it's -56. This is the change in H of neutralization plus the change in H of dissolution, which I'm just going to write D. So I got to worry about the energy change of dissolving. And so you know that's negative 56, so you infer that that one's negative 14. Okay. In this one, with this weak acid, the HCN, you go change in H of neutralization plus the change in H of ionization. I got to break this hydrogen free first before I form the hydronium ion. Okay, so I infer, because he's negative 56, I infer that he's positive 40. Now, might just come down here and try to explain. Hopefully you got like the gist of it. There's an answer over here which you could pause your video on and do that. Here's an answer that I wrote out for it. I'm not going to spend time on it. I'm just trying to get you to learn how to write answers like in so much detail. What I'd like you to just think about is if I draw out acetic acid, okay, also known as ethanoic acid, most of it, okay, I'm drawing out the whole equilibrium. Okay, this is the equilibrium in when you draw out their structures. And I got to, if you think about it, most of it is going to be in this form. Okay, it's a weak acid. I got a bit extra knowledge knowing that it's particularly weak, although you guys after the whole term should be comfortable with how weak it is. Its Ka is quite low. Got to break this bond. Got to form this bond. Automatically, there's an enthalpy change associated with that. There's probably more to it that you can go dive into. You got to, you got water. They're dissolved, right? So you got water that's interacting with this. This is going to be hydrogen bonds. You got water over here interacting with this as well. Because he's an ion and he's an ion, this is going to be ion dipoles, and this is going to be just hydrogen bonds, H bonds. Okay, and so there's more into it. But if all I can get into your head is that there's bonds breaking and bonds forming, and so there's another enthalpy change, and then remind you of Hess's law, which says basically you can kind of treat them all as separate entities, and then if you know about one, you can deduce the other if you know the overall, right? Like kind of how maths always work. If you know two of the three variables, you get the third variable. Cool. Might pause there, but actually before I go into the really hard question. Right, by the way, this is a really hard question. This is really hard because there's a lot of assumptions that needs to be made, and it uses a KSP value, which you can actually get around if you're smart enough to use an assumption. But anyway, that should say placed. So it's been cut off there. So when a student placed 15 grams, and the hint to that is not all of the 15 grams of magnesium hydroxide dissolve. Reason is there is a KSP associated with it on your data sheet. Okay.